Okay, we're getting into linked lists today. So in this video, linked lists are typically represented with drawings such as the following. Linked lists can be a little tricky to understand, but hopefully I do a decent job here explaining them and why we would want to use linked lists, theoretically at least. There are some practical considerations. Vectors are that is dynamic arrays are generally the preferred data structure in C++ and probably also in other languages compared to linked lists. Okay, so we have this thing called a node, and it contains some data, which is the data 5 in this case. And this second box here, this block, is containing the address of the next node in the list. And there's a starting point and an ending point, and this is an example of a singly linked list. A doubly linked list would consist of arrows pointing in both directions. So if this node also had contained some data that pointed backwards, and in that case there would be 3 boxes. I started down this path not anticipating having to draw too much, but this is another box containing an address, and of course the resize is going to be a pain. So this box contains the address of a previous element. If there was something in front of this linked list node right here, that would be a doubly linked list. Let me just look up an image. Oftentimes you see a dash between these words if you want to be grammatically correct. So this is a doubly linked list. It contains the address of the next node and the previous node. In the case that you are the front node, your previous address points to null. It points to nothing because you are the first node. And if you are the last node if you're the last node, your next member variable, your pointer, and these are going to be member variables next and previous. Next points to null if you're at the end of the list, and previous points to the previous node. We'll be writing code for this, the singly linked list at least. So this is a picture, fairly easy to understand. It's somewhat reminiscent of train cars, the car on a train. They're linked together and they go rolling down the railroad. We're also going to talk about recursion, and linked list. There's actually a link, pun intended, between these two topics, linked list and recursion. You could describe a linked list as a recursive. I don't think it would be terribly inaccurate to think of a linked list as a recursive data structure. It is consisting of these things called nodes, and the nodes contain some data and an address of another node. So it's a bit sloppy perhaps to call it a recursive data structure, but there's definitely some links between these two topics, linked lists and recursion. But in this video, I'll only be talking about linked lists. We'll talk about, probably in a couple of videos from now, we'll talk about recursion. Some folks are already familiar with recursion. A very simple example of recursion, infinite recursion, in fact, is this example right here, which I demonstrated that this leads to with Stack Overflow and infinite recursion error. You would want to wrap this in a condition like if input equal m, like prompt the user to select to rerun the main function, so that wouldn't necessarily lead to infinite recursion. Okay, so in arrays, if we want to insert elements or possibly delete elements from the middle of an array, then this is potentially very costly. And what am I talking about? arrays are contiguous. And what does this mean? Vectors are also contiguous. Let's look at both static arrays and dynamic arrays. What am I saying here? Can involve the movement of many elements. An algorithm for insertion and deletion in dynamic and static arrays regardless. So if I set a breakpoint and examine the contents of memory, it's actually been a while since I've done this for a vector, so we'll see how that goes. So step and step. And before we return 0, which is the next instruction, let's examine the contents of, let's say, ampersand, the address of static array. And we see a 1, 4 bytes. Each of these 2 digits is 4 bytes. If you right click and you say sign to display, it's 1, 2, 3, 4, 5. These are hexadecimal digits we're looking at. If you want to make them 8-byte integers, this is something you can do. Not particularly readable. The 1 byte is nicest to read, in my opinion. 1, 2, 3, 4, 5, but these are contiguous. Each of these positions occupies 4 bytes. And it's either little endian or big endian. You might have expected the 5 here to be over at the right. I forget which is which. Eventually I'll get into that when I teach computer organization. Okay, so let's not step. We see that these are contiguous. So what happens if I were to want to insert the so insertion in a static array is going to push something out. If I insert the element 33 at the 3rd position, then if I shift the 3 over to this position and the 4 over to this position, the 5 is going to be lost, so to speak. So that's one problem, potential problem with a static array. Insertion into a static array. Deletion, say I wanted to delete this element in an algorithm, not just erase it here, but to write a function like if I made this a myArray object, which we talked about in a previous video, myArray of integers. It's not defined right now, but and I say it, excuse me, I call it my static array object. If we wanted to type a dot and we wanted to say delete, delete is a keyword in C++, but so we need to say delete element, so we don't get a conflict there. Delete element at a certain index, like index 1, or not to be confused with the value 1. Let's change that to 11. Delete the index 1. How would we write this code, this function definition in the class called myArray or my static array that I've talked about previously? And would it be efficient? Would it be possible to make it efficient? And because it's an array data structure, that's a limitation of an array. It would involve, deleting this position 1 right here. We could delete it and just leave it uninitialized. We could set the value to 0. Do we want to decrease the size of the array to 4? These are all questions that we hopefully are thinking about. Vectors, dynamic arrays are also contiguous. If we say ampersand dynamic array, let's stop this and rerun it, and let me remind myself of how this works with dynamic arrays. Step and ampersand dynamic array. Oops. So this is a class, so the way it's stored in memory is more complicated. So that's its address. It got changed, and we're looking for these values 11, 12, 13, 14, 15, etc. So changes in multiple places here. Let's say ampersand static array, dynamic array at index 0. I think this gets interpreted correctly. So 0B, 0C, 0D. Now, what are the equivalent values of these in hexadecimal? It's these values, 11, 12, 13. Let me bring up what I'm talking about. So we're in programmer mode in the Windows calculator. The hexadecimal value B is equal to 11. So there's 11, and the hexadecimal value C is 12 in decimal, so 0C, and D is 13, E is 14, F is 15. So you can see in a dynamic array, the elements are also contiguous. It's 4 bytes each, 4 spaces, positions. Not to be confused with the space character. Okay, so that is a pretty detailed and description of this slide, and hopefully it made some sense. This could be an insertion of the, if you have a static array 0, 1, 3, 4, it kind of begs to insert 2 at this position. So this could be some code to do this, and it's tedious. It's clearly tedious. It would be nice not to have to do 3 operations just to insert a single value. Maybe we could just insert a single value, perform a single assignment operation. This is 3 operations because we don't want to lose track of numbers at the 4th position here, 0, 1, 2, 3. So this isn't full yet. There's an empty position, an uninitialized position right here. It's probably the garbage values, these -8, etc. This type of stuff that you've seen before. So yeah, I also mentioned that this is a static array. It can't be resized, and that's a potential limitation as well. But linked lists do not have that limitation. So the word nodes. Node is quite a general word. And if we look up a definition of the word node, we see a point at which lines or pathways intersect. Okay. Lines or pathways. In telecommunications, this is a very big word. An end point, either a redistribution point or an end point. And this is related, it's a big word to know, node. So can we see a nice definition? There's a technical definition, botany, anatomy, physics, mathematics. Mathematics is probably the closest. A network is a series of points or nodes interconnected by paths. So it's not the easiest thing to define. I think Merriam-Webster's has a decent definition. A point at which parts originate or center. I mean, we could just look at pictures of nodes and get an idea of what they are. It's not like kind of similar to lymph nodes. And there's something called node.js, which is related to JavaScript. Or maybe it says node.js. All right, without trying to define what a node is, I mean, this is one definition. The contents of a node consist of data and a link to another node. Okay. And we are going to use pointers. So the link is more or less synonymous with pointer type member variable, which is an advantage of using C++ to learn about this rather than Java or Python, in my opinion. This is my informal definition. All right, many uses of this network topology. This is a use in physics that's dear to my heart. Orbital nodes. It's related to quantum mechanics. Okay, this just mentioned node.js. Here's a picture of a singly linked list. This is airports. It makes more sense. It's a lot more intuitive than these numbers that don't necessarily have any meaning or context. So we go from Los Angeles International to Minneapolis St. Paul Airport, and then we go to Atlanta, and then we go to Boston. And these aren't, it's worth pointing out that these aren't arranged in any, this example isn't assuming any, it's not supposed to indicate the geographical relationships of these airports. You know, Los Angeles is over here. Minneapolis, St. Paul is up here, and Atlanta is down here, and Boston is up there. So that's just possibly a good thing to point out. Don't worry about that so much. And it also gets at the point of how linked lists are stored in memory. So a first node of a linked list of integers could be these 4 bytes. And then you scroll down here a lot, and then these 4 bytes are the next node. So we're using dynamic, we're going to use heap memory allocation, what's called heap memory allocation, and we're going to dynamically allocate memory in a C++ program whenever we create new nodes in a linked list, and they aren't contiguous, and that is a potential great benefit because if you have the first node's data right here and the first node's data right here, you don't have to worry about overwriting whenever you insert a new node. If the node data, if the data of the 2 nodes were in these 2 positions next to one another, you don't have to worry about overwriting. That's a potential advantage of linked lists. And here in a bit, we are going to write a class called node, and we're probably also going to write a class called linked list, and a linked list consists of nodes. So it's going to say node star hit the head of the linked list or the front of the linked list, if you like. And we're going to say node star front and back, or equivalently, synonymously, you could say head and tail, or last, front, head, first, stuff like this. We'll want to at least include a pointer to the next node in a list, and we'll also want to, let's just use integer data here. We could use templates and say template type name T, and make our data of type T so that we could represent strings such as these LAX, MSP, ATL. But I think I'll probably not use that approach just because templates can be kind of a pain. So we'll probably just use integers, and you could change your linked list to be template type name T later if you like. Okay. So code for a node. Yeah, here we go. I'm making it a struct. So by default, the member access is the member the access modifier is public. Okay. Some people call this info, int info, the info in the node. And we include a link to the next node. So this is the heart of a linked list. It's really simple. It consists of two member variables. It doesn't have any member functions right now. This is the end of the definition of the struct for now, at least. So let me copy that. And link. Maybe this is where they came up with the name for a certain video game character. Two member variables. So we can make objects of this class, of course. And we're going to collapse the linked list for now. So let's get rid of this array stuff, both the static and the dynamic arrays. So node, first node. So we haven't written a constructor function up here, but we could if we wanted to, and we probably will, but I'm just declaring a first node. First dot data equal 42. The numbers are arbitrary here. First dot link equal. Well, let's think about this. So at some point here, I'm going to bring up diagrams.net and be making some boxes. Okay, and hopefully it won't be too painful. So I have made a first node. This is first. Yeah, let's gets to what I was talking about painful. First node. The first node consists of the data, which is in this case 5, more pain. The data is 42, or whatever number you like, just so long as it's an integer type. So 42 is the data, and the moment this is the first and only node, so the link to the next node or a previous node, depending on which direction you want to go in, if you want to go left to right, so to speak, or right to left. This is an arbitrary thing in the computers, from the computer's perspective. You could go top to bottom, but maybe that makes you think of a stack instead of a list. And we'll talk about queues later. Queues are usually thought of horizontally. Okay, so a link to the next node. I've only created one node, the first node. So the link is pointing to the null pointer. So null pointer is a zero, the zero address, 0x00. This is 64 bits, so it's 16 bits. So the memory addresses, 16 bytes, are the zero address looks like this. The 0x indicates hexadecimal. Okay, so now if I make a second node and I insert it after the first node, so if I do this, I say this is the second node, it contains negative and 23, the data, and there, so I'm just going to make this node right now. Node second dot data equal negative 23. Very important that I get that value correct. It's a joke, of course. Now we have a decision to make here. Do we, and it's an arbitrary decision. We could say, do we want this node to point back at this node like this? we called it second, so it will probably make, but we do want to connect them. We want to link them because this is a linked list. Uh, it's probably more reasonable to make the first node contain the address of the second node. So how does this look? Well, second points to, there is nothing after second right now. Yeah, that's just a choice I made. So at the moment, second points to null, the null pointer, 0x00. It points to nothing because there's nothing after it. There is no third node. First points to the address of this node. So can I do that? So I can't yet in this program, I can't say here address of second because there is no second yet. Second is undefined. It gets defined right here. So when I create the first node initially, it's going to point to the null pointer. Its link is null pointer. But now after I've created the second node, I can say first dot link update the link of first node to point at um, contain. I kind of get sloppy with my speech here. The address of second node. So first dot link equal second, excuse me, the address of second. Okay. So this is a legal statement. It is legal. We'll be using pointers here soon, and pointers can be very convenient, and I use them predominantly. But this makes sense. We declared that nodes member variables are some data and a link, which is a pointer type, a pointer to another node star. Okay. So let's test this, and well, first let's see if any errors occurred. Notice that if I say equal second, this is a problem because second is a node type. It's not a pointer to a node. The address of second is an address, and that is, remember, a pointer, as I say in the slides at some point, a pointer is just a variable whose values are addresses. Just like integers have values, uh, integers can be the values -2, -54, 544, 65. Pointer type indicated with an asterisk in C++ and also in C. It must be an address, and we use this ampersand to indicate the address of. Remember, that's not to be confused with double ampersand, which is the logical AND. It's also not to be confused with the single ampersand, which is called the bitwise AND operator. Or maybe I say not the bitwise AND, just in case. I doubt anybody would make that mistake. Okay. So are we running without generating syntax errors? Yes. Can we verify that the contents of the nodes are correct? We have this picture here. So what can we say? See out first dot data. And do we see 42? Yes. How about if we say first dot link? Yeah, I guess that's a decent idea to do. It's a memory address, hexadecimal memory address, 16 digits long, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Again, that's because this is 64-bit. If you change this to 32-bit, which is for some historical reason called x86, the 8086 Intel processor, it's now 1, 2, 3, 4, 5, 6, 7, 8 digits long. But we'll usually use 64-bit. Okay, so the address of the second node, are these two things the same? Yes. Okay. C out second dot data should print -23, and it does. There's another way to do this. We can say cout first dot link dot data, and you see that this does indeed appear. Excuse me, arrow data, and that's quite an important point to point out. And you notice that if you type a dot here, there's an error, and it says expression must have class type, but it must be an object of a class, but this is actually a pointer. First dot. If you type a dot here and you hit tab, Visual Studio auto corrects you to what is called the the arrow operator. So to access members of an object of a class, we use the dot operator, but to access members of a pointer, we use this arrow operator. This gets to the dereference operator, and I will assume some knowledge of pointers here, but let's go ahead and play with that. So int a equal 5, int star pointer to a is equal to the address of a. So cout pointer to a is going to be containing the address of a. So 7 blah 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 734. If we run this again and we say cout address of a, and these two are the same, of course. How do we print the value of a? One way to do it is, of course, this. Okay, 5 is the value of a, but another way to do it is to use something called the dereferencing operator, the dereference operator. So star is not multiplication, asterisk is not multiplication here. This is the unary, it's a unary operator. It takes only one operand, which is this pointer variable. Notice that we can't do things like star 5, because this doesn't make any sense. We need to say 4 times 5. It's interpreted as multiplication in this case. But when you apply the asterisk operator to, or the star operator to a pointer type variable, what happens? You print the value 5. Okay. So in the context of in the context of nodes and linked lists, we could say there's some other syntax. We could say, I forget exactly how it works. Well, let's keep it simple. We're just wanting to print second dot data, second dot data. So that's the address of second. So that is a pointer type. So if we dereference this star first dot link, I think the order of operations gets a little screwy in that case. Yeah, still. I forget how to explain this properly, but when you're, yeah, let me pause for a minute.